Let's go over Activity 5, Classification with Naive Bayes and Logistic Regression. So question number 1 forces you to basically work through the naive Bayes procedure by hand. We have 10 individuals with the class labels that were given to us ahead of time, and then a combination of 4 characteristics, which we'll just refer to as the generic labels, x1, x2, x3, and x4. Now, what we want to do is we want to use this data to classify a new individual who has x1 of y, x2 of y, x3 of y, and x4 of n here. So which class should we classify this individual into? All right, so to use naive Bayes, what we want to be figuring out is essentially the posterior probability that the individual belongs in each of the classes. Basically, what is the probability given this information that we know about them? So part of the formula that we work through is taking into account the prior probabilities of each class. Now, the prior probabilities is just the overall fraction of individuals that belong to each class, and it's kind of our baseline probability for what we think each class for an individual might be. So it's pretty easy to figure out the prior probabilities. We simply look at the data that's been given to us, and the proportion of A's and the proportion of B's give us the prior probabilities for A and B respectively. So what we would have is 6 out of 10, which would be P of A, the prior probability for A, and 4 out of 10 for the prior probability of B. So this is just the proportion of individuals who have class A in the data at hand. All right, so naive Bayes works by actually calculating the score for each class instead of the posterior probability directly. And that's because it has to make some grossly simplifying assumptions, namely that the appearance of each characteristic, the values of the predictor variables here, are independent of one another. And we also assume a few other things that make the number that we come out basically have to be interpretable as kind of a relative likelihood instead of an actual probability. So we're just going to call this a score. All right, so how do we figure out the score for class A? Well, we know that the score for class A is simply the prior probability for class A times something about the relative frequency of the characteristics, the individual that we want to classify, how often they appear among members of class A in the data here. So what we do is we look at the first variable, the first characteristic of this individual we want to classify, and it's equal to y here. And so if we're coming up with a score for class A, we focus in on just the people in class A from the data that we've collected, and we look at the proportion that have the same characteristic as our individual in question. So we see there's 6 people in class A. 4 of those have yes, just like this person in question. So this will be 4, 6 times, all right, x2 is equal to y here. What fraction of these 6 people had x2 equal to y? Well, half of them did, 3 out of 6. What fraction of people had x3 equal to y who belonged in class A? Well, 1, 2, 2 out of 6, and then times the fraction of people in class A that had the same value for that fourth characteristic, an n, which we see is 3 out of 6 here. So I can replace the prior probability of class A as 6 out of 10, and we can come up with a value for the score. Now, I've given you what the answer is for this, and so we've confirmed that we've done the correct computation. All right, moving on to the score for class B. In order to classify an individual, we need to come up with the score for each of the potential classes to which it might belong. Same sort of process. We take the prior probability for class B, which was 4 out of 10 here, and then we look at of the people in class B, all right, what fractions share the same value as the individual in question for each of the characteristics. We multiply those proportions together. So what fraction had yes? Well, we see that 2 out of 4 did. What fraction had yes for x2? We see 1 out of 4 did. What fraction had yes for x3? We see 2 out of 4. And what fraction had no? We see 3 out of 4. So once we multiply these together, we come up with a score for class B, and we see that it's the answer that is anticipated. All right, so according to naive Bayes, the individual in question would be classified to, well, whichever score was larger, because in some sense it's more likely that they belong to that class than the other. And so we see that the score for A is significantly higher than the score for B, and so it would be classified to class A since its score 0.033 is higher than that for class B, which is 0.01875. All right, once we have the scores for the two classes, we can actually convert those into the posterior probabilities with just a simple mathematical operation. So we started out with prior probabilities that the individual belonged to each class, just the overall frequency of those classes in the data. Given this additional information about the individual, namely their set of characteristics, now what's the posterior probability of each of those two classes? All right, well, the way that we do this is to look at our scores, and if we want the posterior probability for A, we're going to take the score for class A and divide by the sum of the scores for all of the classes. This is just two classes, so our denominator has the sum of just two scores here. If we had more than two classes, we would have to add all of them up together. And same thing here for the posterior probability for B. And let's get an idea for what the posterior probabilities are. All right, so about a 2/3 chance that we think the individual belongs to class A, and a 1/3 chance that the individual belongs to class B based on their set of characteristics. All right, let's imagine that we have a new quantitative variable that we've collected about these individuals, x5. It's numerical. And how do we get Bayes, naive Bayes, to work with this? Well, each of the values of numerical variables are typically unique among individuals, so we have to come up with some sort of simplifying assumption that lets us basically score that component of the information for the individuals for each class here. And so the way that we do this is by assuming that the distribution of any numerical variable has a normal curve here, and so we essentially look at the height of the normal curve to come up with a contribution to the score for each class. All right, so among those in class A, the values of x5 have a normal distribution with this mean and this standard deviation. And among class B, it's a different normal distribution, slightly lower values on average, but slightly more spread out. So the first thing we're asked to do is to make a curve of these normals just so we can visualize basically what's going on here. So the way that we make a normal curve here is to invoke the curve function. And specifically, we're going to make a curve of the normal distribution. So our command is going to be dnorm here. The way I need to fill this out is by actually just having x as the first argument. Now it always has to be like this if I'm making a plot. This is the way that the person who wrote the dnorm function needs it to be. Then we put in the mean, then we put in the standard deviation. And then we're going to say, all right, well, where do I want the left and right limits of the plot to go to and from? And so we can add arguments from equals 0 to equals 30 to get our first plot here. So we're assuming that the distribution of x5 looks like this for individuals of class A peaking at 15, with a typical difference between the mean and the average, the values observed of about 3 here, standard deviation of 2.7. Let's add in this other curve here. Well, we can run a separate curve command. Still dnorm x here. We just put in the new mean and standard deviation. And then what we would like to do is we would like to add this curve to the existing plot. So we'll put in the argument add equals true. And to differentiate that from one another, we're going to give it a separate color, call equals red. So I will run this, and there's the other normal curve. Now, if you're running RStudio so that the plots are actually being embedded into the RMD file on the fly, you actually need to make sure to highlight all the lines of code that build up a plot in order for the plot to be actually constructed correctly. So the last thing we wanted to do actually was to add in a vertical line at this value of x5 for the individual in question. We're going to add a vertical line at 9.1. All right, so we see that, all right, this is the individual's value of x5 here, 9.1. We see that it's quite a bit more likely that they belong to class B, the red normal curve, than in class A here, because the height of the normal curve is much taller for class B. All right, so how do we update our scores to reflect this new information? Well, the way that it works is essentially the score is still just the prior probability times some number that we give based on the fraction of individuals in that class that share a common characteristic with our individual that we want to classify. So while here we were actually looking back at the data and saying, well, what proportion of those individuals in class B had x1 equals to y? What we're going to do is the number that we're going to put in here is just the height of the normal curve here. That's just the procedure. Seems like a reasonable thing to do because the more likely it is, the larger that number is going to be. So what I'm going to do is I'm going to take my old score for Class A. I'm going to copy that down here. My old score for Class B, copy that down here, and just update it by multiplying by the height of the normal curve, which I can get with dnorm at the value of x in question here, 9.1, same mean and standard deviation as what I had plotted. And then same thing for this. I want to have the mean be 10.2 and the standard deviation be 3.4. All right, so this will update my scores to reflect the information in X5. And now what I see is that the classification is actually reversed. The score for Class B is now quite a bit higher than it is for score A, so I would classify this individual into Class B here. All right, so I'm going to put a little comment. We classify this individual as Class B now, given the information about X5. Why did the classification flip? Well, looking back at this normal curve, we see that it's so much more likely to observe a value of 9.1 from Class B than it is to Class A, that sort of flips our whole opinion of what's really going on. There's only a 2/3 chance based on that first 4 variables here that it belonged to Class A, a 1/3 chance that it belonged to Class B, and this looks like it's enough evidence actually, the way the math works out, that it flips the classification around. All right, question number 2 asked us about logistic regression. Logistic regression can be used to classify an individual into one of 2 classes. It's only for a 2-class problem. And imagine that we're given some sort of output from R where we're trying to classify individuals into Class A versus B using 2 predictor variables, x1 and x2. So here's the regression output, and we're asked, all right, well, what's the model predicting? The probability of being in Class A or the probability of being in Class B? Well, the way that R works is it looks at the alphabetical order of the classes that you're trying to predict, and it's going to build the model to predict the class that comes last alphabetically. So B comes after A, so this will be the probability of being in Class B here. It's last alphabetically. All right, according to the model, what is the probability that an individual belongs to Class A and to Class B, given that the individual has x1 equals 308 and x2 equals to 124? All right, so how do we get the predicted probabilities out? Well, I'm going to start with B first because that's what the model is predicting here. And I'm going to do P of B, left arrow, and then the equation for the logistic regression here. Now, what is that equation? It's pretty complex. We have to take E and raise it to some power, and then divide that by a pretty big fraction, 1 plus E raised to that same power. So what is this power? Well, I simply look at the intercept. I'm going to copy and paste this. Then I add that to a weighted sum of the predictor variables. So I would add the coefficient of x1 times the value of x1 that I'm looking at, which is 308. Then I'm going to add that to the coefficient of x2 times the value of x2 of this individual. All right, now since I've just written the expression in the numerator here, this same expression appears in the E in the denominator as well. So there's my really quite long expression that gives me the probability. So that's P of B. What's the probability of A? Well, it's just 1 minus the probability of B here. The 2 probabilities have to add up to 1. So the probability of not being in Class B, or probability of being in Class A, is just 1 minus that. All right, so let's look at these 2 probabilities. How do we classify it? Well, we classify it to whichever class has the higher probability. So we classify to Class A because the probability is higher. All right, so next question. Bob has an x1 value of 300. Jane has a larger x1 value, 400 here. But they both have identical x2 values. So what does the model say? Who has the higher probability of being in Class B? All right, well, that's exactly what the model is predicting, the probability of being in Class B. So we can look at the signs of the coefficients of our model to make this decision here. So we look at the coefficient of x1, and it's positive. So what that tells us is that among otherwise identical individuals, with regards to the other predictors in the model, in other words, identical values of x2, the one with the larger value of x1 is going to have the larger probability of having that level of interest, the one that comes last alphabetically, which is class B in this case. So Jane has the higher probability of being in class B because the coefficient is positive. Coefficient of x1 is positive, and Jane has the larger value of x1 with identical values of x2 with Bob here. All right, well, Eric has an x2 value of 300. Jack has a larger x2 value here, but they both have identical x1 values. So what does the model say? Who has the higher probability of being in class B? Well, we look back at the coefficients of our model here, and we see the coefficient of x2 is negative. So what that tells us is that among otherwise identical individuals, in accordance with the other variables in the model, meaning equal values of x1, the one with the larger value of x2 is going to have the smaller probability of the class of interest, the class that the model is trying to predict here, which is class B here. So what we find is that Eric will have the larger probability of being in class B because the coefficient of x2 is negative, and Eric has the smaller value of x2. Great. Question number 3 asks us to explore the junk data in Reg class. Now, the goal of this data set is to develop a model that classifies an email as either junk or safe, and the results are in column junk here. If we look at the variables we have, junk is a factor with 2 levels, junk and safe. Safe comes last alphabetically, so when we build a model, it'll be predicting the probability the email is safe. And our predictor variables are basically word frequencies, the fraction of words in the email that match up with one of these words in the columns, and then also stuff about punctuation frequencies, hashtags, $signs, etc. All right, question A says, if the naive model is used for classification, what does it classify every email, junk or safe? And what is its successful classification rate? All right, well, the naive model simply says whichever class has the majority, that's what I'm going to classify every single individual to be. So in this case, we see that safe is represented more often in the data. So the naive model is going to predict every email to be safe. So naive model predicts every email to be safe. So it's going to make a lot of mistakes, but it'll get a lot of things right. It's going to have 2,788 successful classifications out of a total of, well, however many rows there were in the data set here. The successful classification rate would be 60.6. Now, there's actually a really neat way to get this number out automatically. Notice when I just run the command table, it's a vector of 2 numbers here. I can actually divide these 2 numbers by the number of rows in the data to convert those into relative frequencies. And if I take the larger of those, well, that's going to give me my successful classification rate because the naive model classifies everything to be the majority class. So 60.6% successful classification rate. All right, well, what do models have to say about this, naive Bayes and logistic? Question B asks us to explain why the naive Bayes classifier is a poor approach for making classification. And we have a little hint that says look at the distribution of the frequency your. All right, so one of the fundamental assumptions of naive Bayes when it uses numerical variables to make scores for each class is that the overall distribution of the numbers looks like a normal curve for each class here. So, all right, let's just look to see the distribution of the word frequency your. So let's just make a histogram of the values inside the your column, specifically for the ones that we have safe and the ones that we have junk. It needs to be normal for each of the classes under consideration. So let's look at these in turn. All right, so among safe emails, here's the distribution of the word frequency your. Looks nothing like a normal curve. Among junk emails, looks nothing like a normal curve, very strongly skewed towards the right here. All right, so the distribution of the word frequency for your is not well described by a normal curve for either the safe class or the junk class. Thus, the normality assumption behind naive Bayes is failed here. So it may be a poor approach for making classifications. The assumptions are violated. But we know that obviously wrong models can still be useful, so let's go ahead and actually build this model anyway and see how well it does. So we're going to build the model anyway using all variables as predictors. So I'm going to load up the E1071 library, which will give me access to the command naive Bayes. So naive Bayes. How do I fit the model? Well, I want to say the name of the variable I want to be predicting, basically our class variable. That's junk with a capital J. And since I'm using every predictor to help in my classification, I'm going to specify my formula as twiddle dot. Use everything here. What data set does that live in? Well, that's the data equals junk, data frame. We fit it, and now what we want to do is look at the confusion matrix. So I need to make predictions. So let's save the predictions to be the result of running the command predict. What are we predicting from? Well, we're predicting from the model naive Bayes. The first argument is the model. And then we say new data equals, and we say, well, where are the data values for the individuals that we're making predictions for? So just the same data that we just used to fit the model. So we'll make those predictions, and then we're going to make a confusion matrix. Now we're going to make this using the command table. The first argument of table are going to be the actual classes. So that's going to be the values inside the junk column in the data frame. And the second argument are going to be the predicted classes according to naive Bayes. So let's make sure I don't have a typo. Let's look at the confusion matrix. All right, so I correctly classified a bunch of stuff as junk. I correctly classified a bunch of stuff as safe. But there's some errors here, the off-diagonal elements. If I want to know what the successful classification rate is, I basically need this number plus this number divided by the number of classifications that I made. I can quickly get that out if I say diag CM. That gives me the diagonal elements going down and to the right, my successes. So if I take the sum of this vector here and divide by the number of rows of junk, the number of classifications I made, that's going to be my successful classification rate. So, all right, it looks like the successful classification rate is better than the naive model because it is 71.35% instead of 60.6%. So even though we have assumptions being violated with the naive Bayes procedure, which itself makes grossly simplifying assumptions about the world, we still see that this obviously wrong model, is better than no model at all. All right, well, what about a logistic regression model? In part C, we're asked to explain why a logistic regression model would be a poor model to describe how the probability of an email being safe or junk varies with the predictor variables. And we're given a hint that, once again, look at the word frequency your and look to see if just a simple logistic regression predicting safe versus junk from this one variable looks like it is well described about that logistic model. So let's fit that simple model here. We'll invoke the command glm. The formula we want to be using is junk twiddle your, because we're predicting jump just from your. That lives inside the junk data frame. And to make it do logistic regression, we have to add in that argument family equals binomial. All right, so we fit the model. Let's run check regression to see if this model is okay. Now the output of check regression gives us two p-values. We're only going to focus on what method 1 is. It turns out method 2 is really hard to pass. We're typically going to fail that and get a p-value less than 0.05. But with so many data points, it's super easy to fail it. We're not going to worry too much about it. Method 1 is a really easy test to pass, and so if we fail it, then we know that the logistic model is pretty much an obviously wrong model. And we do fail it here because this p-value is less than 0.05. So the p-value of the method 1 goodness of fit test is less than 0.05, so this is an obviously wrong model. That curve, that logistic curve, doesn't really provide a reasonable reflection of reality, but obviously wrong models sometimes are really quite useful, so let's just go ahead and see how well a logistic regression would do. So let's build the model using all the predictors now. So I'll just copy my glm command and replace twiddle your with twiddle dot, all the variables. We'll fit that model. We get a little warning message saying that fitted probabilities of numerically 0 or 1 occurred. So it's basically saying that there's a 100% chance of one of the classes or a 0% chance of one of the classes. That's fine. Not really a warning message that causes us any concern. And we're going to report the successful classification rate. All right, so we need to make predictions. And let's create the vector and left arrow it to be the result of running predict on our logistic regression model. First argument is our model. Second argument is the data on which we're making predictions. That's the junk data frame. And when we're making predictions with logistic regression, we actually have to add in a new argument, type equals response, so that it's actually predicting probabilities instead of some other quantity that it deals with. So you'll notice if I just run this part of it, we get numbers between 0 and 1 out, so these are probabilities. Now, I actually need to classify the individuals. I need to basically say they are classed safe if this value is bigger than 0.5. That's the one that comes last alphabetically. And it's equal to junk otherwise. So I'm going to use the if-else command to help me out here. Remember, the if-else command will go through each element of a vector and return something based on whether or not the logical condition is true or not. So what I want to check basically is whether or not this predicted value is at least 0.5. If it is, then I want that to be classified safe. Otherwise, I want it to be classified as junk. So you'll notice if I run just this if-else part, we've converted everything to junk and safe, and so I can save those as my predictions. And so now I can get my confusion matrix by making a table of the actual values as the first argument, and then my predicted values as the second argument. So let's look at the confusion matrix. Still a few errors, but looks a little bit more promising. This was a much bigger number with naive Bayes. Let's get the successful classification rate by taking the sum of the diagonal elements of the confusion matrix, dividing by the number of predictions that we made. And we find that, wow, this is actually really quite effective. Obviously a wrong model. The probability has a much richer variation with these predictor variables than what the logistic regression model actually can handle, but it's still really quite useful here. So the successful classification rate is a whopping 93.1%, which blows away the naive model and naive Bayes. All right, pretty nice. All right, last question deals with the iris dataset. This is one of the classic datasets in data mining. We're asked to classify flowers into one of 3 species based on 4 characteristics of the flower. So what we're going to do is actually add in a little R chunk here. I'm going to call it iris, and let's actually load up the iris data. Now this comes default in R, it's so common. Let's just look at a few of the rows of the data frame. We're given information about 4 physical characteristics and then the species. If we want to look to see, all right, well, what are the species? We have Setosa, versicolor, and virginica. All right, so question A asks us, why can't we use logistic regression here to classify the flowers? Seems perfectly reasonable, but why doesn't it work? Well, remember, logistic regression is only able to be used for the 2-class problem. Here we have 3 classes. Logistic regression can't handle that. So there are more than 2 classes, so logistic regression won't work. Now, there is an extension to logistic regression called multinomial logistic regression that can do this, but we're not going to talk about that in this course here. All right, question B says, how would the naive model classify each flower? What would be the successful classification rate? Well, let us look at the summary here. We see that, oh, all 3 classes are equal frequency here. So the naive model would basically just pick one and say every single flower is that species. So let's just get a table of the species here so that when I knit it, it's there. So all classes appear with the same frequency. Naive model would pick one of them and classify every flower as that species. Regardless of its choice, though, we see that it's only going to get 50 out of the 150 right. So the successful classification rate would be 1/3, or about 33% here. All right, so can we come up with a model that beats the naive model? Well, naive Bayes can handle multiple classes. Absolutely no problem. We just have to come up with a score for each class that makes the number of computations we have to do a little bit more in depth. But hey, R will do all of the naive Bayes for us. Let's just work with the results. So let's run the naive Bayes algorithm. So the command is naive Bayes. What are we predicting? Well, we're predicting species. What are we predicting it from? Well, all the variables. So twiddle dot, it lives in the iris data frame. So we fit it. We want to get the confusion matrix, so we want to make predictions here. We'll predict from our naive Bayes model on the new data equals iris here. And then we want to get the confusion matrix. So we'll make a table of the actual species and the predictions. Take a look at it, and then looking forward, we're going to look at the successful classification rate. So we're going to take the sum of the diagonal elements, the confusion matrix, divide by the number of predictions that we made, and let's see the results here. So wow, the naive Bayes algorithm actually succeeds phenomenally well. Notice that of all of the 50 setosas, the predicted values are all setosa as well. 100% successful classification rate for that class. Versicolor, well, pretty good. 47 out of the 50 times, it correctly classifies that with 3 misclassifications going to Virginica. And then same thing for the Virginica class, just swapping those predictions with Versicolor here. So naive Bayes actually really does fantastically well. Naive Bayes performs very well for classification with a successful classification rate of 96%, blowing away the naive model at 33%. And also, it correctly classified every setosa. So it's kind of interesting. All right, so that is our Activity 5, your introduction to classification with naive Bayes and logistic regression.